Yes, I would like to discuss with you about uh, a new approach to derive some response function. As you know, response function is probably one of the most important concept, I believe, in psychometrics, because many things derive from that, including potentially some errors that can be done if you are not able to correctly identify the true or approximately good response function, then you are likely, or you are at risk to badly interpret your data. So it's interesting to examine several potential solutions, several candidates as response functions in any situation. And it's also important to know how to derive and to construct such response functions, so that we get flexible enough response function. And I would like to show you an approach that I've been developing along the years for deriving and constructing a response function. I will give you examples in the cumulative field and in the unfolding field, because I know we are in the house of unfolding here at Georgia Tech, so it's important to give also an example in that field. I don't know if you know this guy, Verhulst. He was a Belgian demographer, and he was also a student of Quetelet, another famous Belgian statistician and demographer. And Quetelet was his supervisor, and he asked him to find an alternative to the exponential to model growth, because he had found out that in many cases, growth was reaching some kind of upper limit, and of course the exponential was not suitable to such cases. So he asked him to work on that, and Verhulst had this idea to define it as a differential equation. In this form, he was looking for a function that which variation was proportional to itself, as is the case for the exponential, but he added a very smart penalty factor here to make it so that when approaching one, the function was simply not varying anymore. You understand that in this case, well, and there is a typo here. It should be f of x. Anyway, he combined both f and 1 minus f of x here to get a definition of this function variation that would be confined to the 0-1 interval. And the solution of this equation is well known. It's the now well-known logistic function, from which a number of item response models have been derived, and which also had an impact on the regression field, as you know. And the Rasch model was derived in based on the logistic model. Note that I decided to write it here in complementary form from reason that should be clear in the following. Of course, you know the 2-parameter logistic model, which just extend it with a scale parameter here, and you know also the 3 and 4 parameter logistic models, which add potentially a lower asymptote and a higher asymptote. Here again, I write it in complementary form, not the usual form that you will find in handbooks and papers, but under this form, it will fit in the framework that I would like to present. Okay. So you know this very well, but what I would like to do now is to propose some kind of extension. In some way, the logistic might be seen as describing the growth of one process, of a single process. And generally, we use it for each item separately. What I would like to present is an approach where the response to a single item is actually determined by 2 processes which can be in interaction. One of them, one can have an impact on the other. I'm just representing here a very simple two sub-processes case, but you can easily imagine how this could be generalized with three or any number of sub-processes, okay? Each process is likely to have its own growth, like a logistic growth, but each process is likely also to have an impact on the other process growth, okay? All those sub-processes, as the response itself, are dependent upon a common latent dimension, and the interaction is likely to be of two nature. It could be activating or it could be inhibiting. So both kinds of relationship can be imagined in this very simple context. Please note that this plot might be a little bit misleading if you have some experience in the structural equation field or in Bayesian network models. This graph is actually representing how one process's variation is likely to have an impact on the other process variation. So it's all about variation and differences, okay? It's not the intensity itself that is modulated, but the variation of each process being modulated potentially by the other, okay? Let's imagine maybe the simpler case within this generic framework. Imagine that we have a sequential model, two processes, one having an influence on the other, a positive, an increasing or activating relationship or impact on the second one. The first one has its own growth process, and the second one is under the full influence of the first one. Y is the response, but in the following, Y will be a simple copy of X2 actually. So we could imagine here some more complex type of response function. I mean, between the last sub-process and the response itself, but I want to keep things simple here. One way to translate this graph into equations is to write the variation of the first process here as being proportional to itself, which is just another way to define an exponential growth, okay? And the variation of the second process here is defined as being under the influence of the first process, potentially up to some delay parameter. Well, I call it delay, but you can see it also as a shifting parameter, because this delay might be along some control variable that is not necessarily temporal by nature. So essentially, it's a shifting parameter. Okay. So it's a first model, a first proposal, and you could easily imagine how we could generalize this kind of sequence with 3 or 4 or any number of steps. And under this form, what we have formally is a kind of simplex network. But one problem with this first definition is that probably it's not well suited to the kind of data we have. Actually, this kind of equation has a well-known solution. What you get when you integrate such a system is just a linear combination of exponentials. Okay, and this is well known in chemistry, for instance, where you study how some product tend to increase the production of another substance, and so on in chain. And we don't want such kind of solution, because our data are bounded by nature, either binary data or continuous bounded scales, as I will talk about later. So we need to introduce some kind of constraint by using the very same trick as the rules did. I mean, for the first and the second equation, look how I simply had some penalty factor here, ensuring that x1 and x2 will not go above 1 in both cases. Okay, this is just a trick to bound the whole process and the whole growth process so that it lies in the 0-1 range. Okay, beyond that, we can solve this system. And what we find is, well, you can anticipate it on the first one because it is just the definition of the logistic that we already recall in the first slide. But the second one needs a little bit more calculus. And what you find by integrating both is, first of all, of course, a logistic, again, written in a complementary form. And what you get for the second one is, well, kind of a logistic, but with an exponent appearing. Probably we could call it a generalized logistic because of this exponent. And this is not a new function, actually. It has been used in the logistic regression field by Richards in 1959. And in some way, it embeds both the RASH, the 2PL, the 3PL, and also the logistic positive exponent model, if you know it, by Samejima, under a form that has been described by both Ferrine and Bazin in 2010 under the name reflected logistic positive exponent model. This is the 1- here. And aside from that, you can imagine how this exponent introduces some kind of additional flexibility in our modeling, and potentially some kind of asymmetry in the design of the response function. So it's interesting enough that this derives from a reasoning on variation and from a reasoning where processes are chained together, because in some way it introduces a potential new interpretation of classical models. You can see some classical model and you can derive them from this logic of a sequence. And as far as I know, this has not been pointed out in previous work, that because items are generally modeled separately, each of them having its own logistic, but there is some room for other way of doing so, and modeling potentially several items in the same time by assuming that they actually form some kind of sequence, but more on this later. Anyway, to understand the impact of this sequence, I draw here the first and the second equation. I mean, the first and the second process, which I call the parent and child process. And you can see how the slope of the first one can be modulated, of the parent process can be modulated. And this has an impact on the second one through the beta parameter, which is the real induction or implication, I don't know how to call it, parameter. This parameter represents the way x1 has an impact on x2's variation. And of course, this impact can also be modulated in such a way that will create some kind of asymmetry up to some delay that we can also set here on this parameter delta. Okay, so what you see is basically how two processes are modeled together, chain with a sequential relationship, and this gives rise to some asymmetric response function, so to some additional flexibility in our models. You can ask if this kind of chain can be generalized. I mean, the first process generates the second one, and the second generates another one, and so on. Actually, to tell you the truth, this becomes quickly very tricky. I mean, the integration is far from trivial and implies the incomplete beta in particular. And so it has no analytical form. So what I did here was, and what you see with the gray curves here are simply numerically generated by numerical integration. And what you see as the dashed line above the gray lines is simply the previous solution, this solution that we get in the first step, but it is flexible enough to finally approximate pretty well all the consecutive steps in this sequence. So it's a good model for which, if you have a beta parameter, the induction parameter, being above 1, then you see how this translates into an acceleration of the slopes, of the consecutive slopes, while when this parameter is below 1, it is the inverse. I mean, the slope is kind of dampened by this kind of value in implication. So it's very interesting because it has been pointed out by some authors, first by Samejima, but also by Daniel Boltz, which talks a lot about this topic. It has been pointed out that in some cases, you may have some kind of correlation between difficulty and discrimination in applying the 2PL model. And from their view, it is substantial, not accidental, but substantial. And it seems to occur when indeed some kind of accumulation of complexity is occurring in some way. The more difficult items accumulating some kind of additional processes, the response in the more difficult items seems to be determined by several components and not only one. So it is at least their interpretation of this phenomenon, which is likely to occur in both forms, the left one and the right one here. And I have applied this to a data set on which I'm working with Arabic Institute in Paris. They are designing a test of proficiency in Arabic language. And so they have a lot of items. I just show you here 15 items, but I want to show you what it gives on such data. Bolt reported that on language items, it is often the case that as you consider more difficult items, the slope or the discrimination tend to be lower, actually. And this is more or less what we see here. And the graph is a little bit convolved, but if you look at the blue curve, the blue curve is the model that I've presented in the previous slide, and it's flexible enough to be able to capture here this very high slope, and on the other side, a very low slope here, a low value for the slope or for the discrimination. And if you look at the gray curve, I hope you can see it, guys, because it's a little bit small and tightened, but the gray curve is the 2PL. And if you look, the 2PL tend to be a little bit beyond the blue curve on the first items. And as you go further with more difficulty, the gray curve, so the 2PL, tend to be a little bit above the blue curve. Okay, so it means that there is some kind of asymmetry and slope variation that the 2PL is unlikely to capture. So this additional flexibility is indeed interesting to exploit in modeling. Another way to view the bias introduced by the 2PL when indeed there is some kind of dissymmetry or asymmetry is to look at the estimates of the ability with one and the other model. The 2PL is here, and the model that I called cascade of generalized logistic. Kogel means cascade of generalized logistic. When you look at the relationship between both, the 2PL tend to overestimate a little bit the aptitude in the lower score and to underestimate the aptitude in the higher score. So this is another way to see how it's interesting to try to exploit this additional flexibility given by this model, keeping in mind the interpretation of some kind of accumulation, I don't know the word in English, accumulation of several component or sub-processes underlying the final response. So this is the first example I wanted to give you. Okay, look at the clock. It's okay. I would like now to show you an extension of that or variation of this reasoning. Now introducing some kind of inhibition between the process. Consider two processes again, but the second one will have a negative impact on the first one's variation. Okay. The second one has its own growth, okay, that we will model in a logistic way as previously, but it will have a negative impact on the first one. And the response is simply a copy of X1 this time. Now, what does it change in our implementation in terms of differential equation? The first one variation, the first process's variation is modeled as being first proportional to itself, very much like an exponential, but we add an additional inhibition term under the form of x2 and a minus sign, gamma is positive, and this influence is likely again to manifest itself through some kind of delay or shifting effect or parameter here. While the second one is simply an exponential growth, it is simply proportional to itself. Its variation is simply proportional to itself, which is just another way to define the exponential. But again, we will have to use our trick to make it sure that we won't go beyond or above 1 in this kind of models. So we use the very same trick here. A little bit more complicated because we both add a penalty factor for the process not to go above 1, but also we have to introduce a very similar constraint to prevent the process to go beneath 0, under 0. It's always the case here that on the first term x1 is present, so we know that when x1 is null, then the variation is null, but this term had no x1 factor added to it, so we introduce this constraint here. No need to do so on the second one, only the penalty factor to prevent from the process to go above 1. So the second one is obviously again a logistic, and this process which have a logistic growth will have a negative impact on the growth of the first process. This is the basic idea. Upon integrating this system of equation, here the function, the second you recognize, of course, the logistic, the classical logistic, but the first one is the new one, and you see how it's a ratio of exponential, but with an exponent on one of the terms here, and the gamma, recall that the gamma parameter is the parameter that controls for the inhibition, so we will look at its impact pretty closely. Basically, you want to reparameterize a little bit just to have something that more closely resemble to what we are used to in item response modeling. I mean, reintroducing in place of T1 here, which is just an integration constant, delta or a linear combination of delta. This doesn't change anything on the flexibility of the model, but is more interpretable. And when we look at the impact of the inhibitive or inhibition process, which is controlled by gamma, you see how when I increase the importance of this inhibition, we get a whole series of unimodal function, potentially non-symmetric, potentially somewhere between a cumulative and unfolding model, with a whole continuum between them. So it's pretty interesting in terms of flexibility to have this in our toolbox. We can try to see how this is suitable and usable on real data. I will consider in the following two examples, which are expressed not in terms of Likert responses, but in terms of continuous responses. So a potential choice as a distribution for such response is the beta distribution. The beta distribution has two parameters, which I call the acceptance parameter, because it tends to give more weight, more density to the higher value of responses. And the second one tends to give more weight when I increase it to the lower value of acceptance. So they are easily interpreted as acceptance and refusal parameters, respectively. And you have to remember that the beta distribution has an expectation which can be expressed as a function of f, m, and n as a simple ratio. The ratio of the first parameter to the sum of both the two parameters of the beta gives you the expectation, which gives us a nice way to recover our solution function in terms of the expectation of some distributional model. If you see how all this is constructed. So this is just a way to plug our function here into a distributional model so that it becomes the expected response function within this model. This is the basic construction. Note that within this generic model, you can set a number of constraints which would give you in this restricted form the beta response model that we proposed with Dauvier in 2007, up to some over parameterization here. But we also can get almost the same model that I proposed in 2014 as the beta unfolding model, up to the +2 constant here, which was not included in the previous model. Actually, this model closely resembled to Jim's proposal in terms of unfolding model, and also to the hyperbolic cosine model by Hendrich. So it's pretty interesting to see this appear within this construction up to some additional constant here, but anyway, it's pretty close. And within a framework that, in my view, makes it a little bit easier to interpret. Anyway, this is the model integrated within a distributional model. I won't go into the details, but because the beta has two parameters, you have to model not only the expectation, but also the variance. So there is a specific construction in this model that helps you decide how you want the variance function to be defined, purely symmetrically or somewhat asymmetrically as desired. This poses a number of problems that I won't discuss here, but be aware of that simply. Okay, I just skipped that part. And I would like to show you the first example, behavior change dynamics. can be modeled in terms of an asymmetric unfolding model. I don't know if you know this clinical psychology model named the stage of change model by Prochaska and colleagues. And they describe 5 stages of change. For instance, when you quit smoking or when you quit drug in many types of drugs. Actually, this model works well. And they define 10 processes of change, some of them being more cognitive by nature and other being more behavioral by nature. And what they discovered is along the stages, people tend to use more cognitive processes in the beginning of this journey and more behavioral processes in the end. So we have an intuition that probably there's some kind of cognitive behavioral continuum behind that. And it is very tempting to try some kind of item response model with a latent dimension to be recovered. And one question you may have in this field is, what is the relationship between all those processes? Is it that the first processes generate the following in a sequence, as we discussed before, or is it in the first part of this talk, or is it that the first process generates the following, but each process in turn will play the role of an inhibitor on the previous one? This would be meaningful, because when actually you have taken some action to quit smoking, you don't need to think that your behavior is really terrible or is really harmful to the environment or your family and so on, because you are quitting already. So it's meaningful to think in terms of an unfolding model and not a cumulative model. I discussed this point many years ago. Anyway, we looked at this many years ago, but here re-examine with this new unfolding model, a non-symmetric unfolding model, more flexible model on data that are basically continuous bounded data collected on response scale that goes from 0 to 100%. We tested 3 different models: the cumulative beta response model, the beta unfolding model, which is symmetric, and the last asymmetric beta asymmetric unfolding model that I just presented. And the best one was the asymmetric model. And it's interesting because what we get here on the right-hand side is pretty close to what the original authors got by simply averaging Likert scores on cognitive and behavioral process, cognitive being in orange here and behavioral being in blue. What they discovered was that cognitive processes tend to peak in the first stages, and behavioral processes tend to peak later in the more active stages. And this is approximately what we get here with a great variety of curves obtained from the very flexible and asymmetric model, but with an important gain that here what you get on the horizontal axis is a continuous coordinate for all your subjects, and also of course a location for your items, so that you see that the cognitive items tend to be slightly on the left, while the behavioral ones tend to be more on the right of the plot. And instead of classifying your smokers in 5 discrete stages, you are now able to scale them on a continuous scale, which is of course an obvious advantage. Is it in some way related to actual behavior, actual quitting, and stages themselves? The answer is yes, because when we look at the distribution of such continuous score along the latent dimension, separated by or distinguished by stages as defined by Prochaska, very clearly in the pre-contemplation stage, people are more on the left. In the maintenance stage, people are more on the right, and all other three stages being somewhere in between. So clearly, this describe in a valid manner what is going on here in the dynamic of behavioral change. I'm just, Jim, looking at the clock to be sure that I have enough time to discuss emotion regulation. Just tell me. Yes. Okay. I keep on, and you tell me. You tell me when I have to stop. Okay. Second and last example of an application of an unfolding model defined this way, and I've used these data set by Koval and collaborator. They have followed 95 people, depressed subjects, for 7 days, and they have asked them to report their emotional state 10 times a day using a mobile device. And they were asked to rate 7 adjectives: relaxed, happy, stressed, and so on. And the main goal was to study the emotional lability among depressed people. They had a number of hypotheses about that, but my interest here is not their goal. It's more, am I able here to model this data with an unfolding model following some reasoning that I would like to develop a little bit. Look at that. Those are 6 sample subjects. Sorry, some words are still in French, but hopefully this is meaningful. What you get here is simply the curve of all positive affects. This is average over the positive adjectives, and the curve of negative affect. So obviously, when the positive affect decrease, then you're not surprised to see that negative affect is increasing, and so on. So there is a natural reflection between both curve each time for each subject. And we would like to model this variation, which is very complex and very noisy in some way. We would like to model that in a suitable manner. You could think of a purely structural manner, looking at PCA, for instance, and you would find sorry, it's in French, an unrotated solution, you would find a main first factor that is clearly bipolar. But if you apply a Varimax rotation, then you would find tempting to think that there are actually 2 independent emotional factors, which in my view is totally meaningless and probably a bad use of the Varimax rotation in this case. But this is being used in many papers, unfortunately. Anyway, this is a first approach to try to analyze such data. Or you may want to have a more dynamic approach and try to model this with longitudinal curves. For instance, here I'm using a generalized additive model. And here in default mode, I mean, it shows us itself the best number of components within the GAM model. And what is probably a little bit disappointing here is that you are missing probably some important feature of the dynamics, of the temporal dynamics with these smooth curves. You may want to add some additional components. Here I put 10 components in it, and so I capture a little bit of the dynamics. And if I put 20 components, maybe I'm better at capturing all these variations. But this is an approach that has been used in many papers. I would like to show you how another approach is possible that is based on a theory. If we based our reasoning on a theory, namely 3 very traditional theory of stress in psychology: the transactional model of stress by Lazarus and Folkman, which assume that your emotional reaction to a stressful event is determined by an implicit assessment of your resources to cope. The theory of learned helplessness, which you know well, undoubtedly, which show how you can get depressed if you're in a situation where you can't cope with the stressor, and the general adaptation syndrome by Selye, which also describe how stage of reaction to stress can be in the order alert, resistance, exhaustion, and depression. If I try to combine all those very classical frameworks in a single view, I would get the following graph, where you have here a bipolar gradient, emotional valence gradient from negative valence to positive valence. And if you think that we are somewhere always in the moderate positive mood, and when a stressor arrives, you are very likely to see your activation state to increase. And then two things are likely to occur. If you are able to cope with the stressor, then you are likely to come back to some kind of equilibrium here near a moderate positive state. But if you fail at coping efficiently the stressor, and this somewhat lasts in time, then you are likely to enter into depression. This is a very simple graph that summarizes pretty well all three theoretical frameworks that I've shown you. And what is important in this view is that it leads you naturally to an unfolding expectation on your adjective when they will be rated by the subject. You are expecting that people on the right will score high on such adjective as serene, for instance, and will score low on adjective like depressed. But people around the middle of the continuum will likely answer on score pretty high on active or stimulated or excited and so on. And you can imagine some kind of mixed states. If you are stressed, then you are both activated and on a negative mood. If you're excited, you're both on a positive mood, but with some level of excitation and stimulation. And of course, the semantic antonyms, bored and calm, will have a response function that are simply inversed here. So these are our theoretical expectation if the previous model correctly summarize what is known from these theoretical framework. This is the result of um, an application of the unfolding, the beta unfolding model, the beta asymmetric unfolding model. But here, the asymmetry is not so obvious. And indeed, the solution is pretty close to a standard beta unfolding model. So not far from the symmetry. You have a pretty nice description here of what is happening. The unfolding itself is not so obvious for many reasons. Not so many people are located really on the negative side. Not so many of them are really depressed, or at least it doesn't last in time. So you have not so many points here on the left side. And from a psychometric point of view, it's a little bit a pain, but a little bit more obvious here, although not so many points here neither. Anyway, at the very least, what you get is a very good unidimensional solution, and this is the main point here. And a bipolar scale, you don't need two factors to model those data. A single bipolar solution is sufficient, and probably with some amount of unfolding in the middle. Anyway, what I would like to show you is just that once you have this model, which, by the way, combines all the measure taken over all the occasions, all the moments, over all subjects. So you are able to reconstruct actually the response moment by moment, day by day, by extracting them from the expectation within these curves. And what you get when you do so, I will skip all those parts. what you get when you do so is that you can model, look at that, the dashed lines is the curve that you can derive from the single or unidimensional unfolding model. Here you can see there's some kind um, of error, of bias. For some reason that is not very clear for the moment to me, the model fails at capturing the higher responses. This is true for positive affect and also to negative affect. So there is some work to do to understand that. But anyway, it is able, with a single dimension, to capture pretty well, at the very least, the variation in emotion. And it's pretty interesting. In the middle range of emotional ratings, it's pretty good at capturing all those variation on a single dimension, just by representing, I'm getting back, just by representing people as a cursor moving along a single dimension. You can get this fine modeling here, which captures the variation pretty well. Here, just looking at the time, yes, I will keep some time for the discussion, so I skip this and just end the talk by saying that this approach I've shown you, which is heavily inspired by physics, implies 4 steps. First, you have to define a number of active forces, which you think that they are underlying the process you are studying. Then you construct a model of their interactions, and a number of possibilities exist, of course. Third, you translate this into a differential equation system, which you have to integrate. And finally, the resulting response function that you get, once integrated into a proper distributional model, then you have, of course, to test it on real data. And this actually defines psychodynamics. Psychodynamics, not psychoanalysis, but psychodynamics in the more physical term, in the more physical sense of the term, is probably what we need more in psychology. I don't know for you guys, but believe we need that in psychology, to be able to model how things evolve and change over time. Well, I'll stop here. Thank you for your attention.
Okay, thank you so much for the talk. Is there any questions?
I have a couple, but I can talk to Yvonne anytime, so someone else.
Yes.
I have a question about you mentioned here, like in this dynamic process, before you apply the model to like any data, you will first like have a hypothesis that the process will be like your variable or some measure will increase or decrease in the sequential process, right?
Yes, that's right. Do you
like if there any like a process first increase and decrease, like they are not continuous decrease only or continuous increase only, can this model like still be applied?
Oh, actually, this is a very good point, because there are 2 ways you can model abrupt changes. You may have this implemented within your item response model. There used to be a guy. There used to be a guy that worked on a so-called Saltus model. I don't know if you know this model. I can't remember his name, Jim, but maybe you can. A Saltus model, Mark something. Anyway, so you can model abrupt change by implementing it directly in your expected response function, but you can also implement it in a different way, and this is actually possible within the beta response model, because I have not I've not talked about that, but unfortunately you won't see this here, maybe here, but actually the distribution around the expectation within a beta response model can be bimodal. Sorry about that. Let me get back to that. Actually, the beta distribution, the beta density, can take actually really a bimodal form, a bimodal shape. And this is very interesting because it can help you model phenomena where people are abruptly bifurcating from one extreme response to the other. And actually, when I began to work on beta response models in 2000s, around that, I was considering this was very unrealistic as a psychometric feature within the model. And since then, I've discovered that it was very relevant, especially in behavior change study, because people are changing in the steps or stages where they actually change, are very likely to bifurcate from one extreme response to the other. So this is another way to implement and model abrupt change within the distribution function and not the expected response function. I don't know if this answers your question. There are actually two ways of doing so.
Yeah, thank you. Are there any other questions?
Well,
yeah, I was going to ask.
Oh, go ahead.
This is really, really interesting. I'm very much intrigued by the asymmetry in the response function that you were showing. I think that shows a lot of interesting promise. But and you did say that when it was replicating the longitudinal dynamics, that occasionally there seemed to be some extreme bias on one half of the. And you mentioned you're still trying to figure that out. I was wondering, is that it looked like most of those longitudinal plots were symmetric, that the red lines were, following in pattern with the blue. Yes. And I was wondering if that symmetry is required by the model.
No, not at all. It's really the data themselves, and it's actually pretty well modeled by Russell's approach to the factor model that he defended was a model where valence is bipolar. The first dimension was bipolar. That is, it's a good summary of the negative correlation that you get between positive and negative affect when you look at the data themselves. What you get are really negative correlations. So it makes no sense to imagine that you have to define two factors in this context. It's just an artifact of applying factor analysis on basically unfolding data that are not suitable to such an analysis. So when you have such kind of nonlinear structure and applying linear models to that, then obviously you need more factors to be able to capture all this information, but the true structure is in reality unidimensional. And as to the failure of the model to capture high response, you have to keep in mind that what the model is modeling is the expectation of a distribution that might be strongly non-symmetric. I'm talking about the beta distribution itself here. And the expectation might lie at some distance of the data themselves. Don't know if I can show you on the plot, but I mean, in a non-symmetric distribution like the beta, the mean, the expectation, is likely to lie at some distance of the mode. Okay, at some distance of the mode. So our curve is passing through this value, but our data are likely to be densely distributed around the mode. So you may have this feeling, at least visually, that the curve is lying away from the data themselves. But part of the phenomenon is indeed caused by the fact that we have here potentially a non-symmetric distribution, and in such a distribution the expectation always lie at some distance of the mode of the highest density zone actually. I don't think this is the only cause of this phenomenon. I think there is something else, but I can't figure out why for the moment. Thank you for your question.
Thanks. Yeah, thanks. That's really interesting.
Okay. Thank you so much for the talk. Because we run out of time, so Jim, I know you have some questions. Probably you can stay longer if Dr. Noel still have some time.
Yes, I have some time, but I don't want to keep you from your business.
Okay. Yeah. Okay. Yeah. Feel free to leave. Yeah. If you have more questions, you can stay longer. Thank you so much.
Feel free to email me if you have some additional questions, of course. Anyway, thank you for your attention.
Thank you. Bye.
Bye.
So, Ivanic, you still there?
Yes, I'm there.
Hey, there was a guy, actually, I studied with him for my master's, named Bob Janarone, and he has this paper in Psychometric on conjunctive IoT models, and it seems like you have your combination or your model where you use differential equations to combine different response functions kind of subsumes his work and does more. So in his work, he might have items that interact.
Okay.
To in a response function, and it seems like that's what one of the things that your model can do. Is that correct?
Well, I don't know if it's a combination of the responses or a combination of sub processes or of hidden processes that finally provokes or explain the response itself. What do you mean by combining here in his work?
So like in a classical test theory sense, you might have, say, two items on a test, but
yes.
The score is really going to depend, if they're binary items, not just the sum of the two items, but also include the product of the responses. And he kind of incorporated that idea into IoT model he referred to as a conjunctive
interesting
response process. But it seems like you're sort of doing that. I mean, when you change one item, you're changing another item in a non-additive way.
Oh yes, that's right. I understand. You mean in the sequence in the first example where I describe a sequence, changing the first one will change all the subsequent items in the series. Right. Yes, I understand what you say. Okay, Bob, who?
So when it might be, I mean, his paper's like, I don't know, geez, going on 40 years. So it might be another thing just showing that your model subsumes a lot of different things that have been proposed over the years, maybe not got so much airtime, but which I think is great. The other thing I was just thinking about, and he was my professor, so I just programmed what he told me to program. But I never really understand his fascination with that. So I was trying to figure out, okay, when you were talking about this model, the cumulative versions of your model, what might I understand the response functions you're getting, but what might I apply it to? And and one thing that came to mind was maybe like order effects. It's like, are you modeling order effects somewhat?
Yes, yes, I think that in some way it could model order effects. Actually, I'm still looking for an example because in this way of modeling things as a series, everything is modeled in the first items uh, because of course you can imagine that all the implication or induction parameters are all equal, and so with a single parameter just changing the first item response curve in cascade is changing all the other response function in one direction or the other, accelerating the slope or dampening the slope. Okay, um, but I'm still looking for a nice application where all this would make sense. I mean, um, I'm looking for an example where some process or some item is provoking or I don't know how to define it, but is the cause, the main cause of a second phenomenon, which is itself a cause for a third phenomenon, and so on. I'm still looking for a good example. It's interesting to know that in the language test, it seems to be the case that there is this strong correlation between difficulty and discrimination. So it might be a good way, a good first idea. But you know, you should to have a clean example, you should find some language exercises where you could argue that the second one has something um, for which solving makes it necessary that you succeed on the first one. I'm not sure it's clear stated like that, but you know, you each of your items in the series should add something to the previous one so that you can understand why a success on the previous one explains success on the other one, at least partly. So um, some more detailed example is probably needed here to argue the relevance of the very principle of this cascade. I've called it the cascade, but
Mhm.
I'm not sure there is a better word, maybe in English, I don't know. Um, So in some way, it is an order effect if you are able to order the basic abilities that are needed um, to succeed on a complex task, on a complex linguistic task. Maybe the items sooner in the series require less sub abilities or something like that. Uh, it's a kind of partial credit in some
Yeah,
way, but
yeah.
distributed over several items. If you could
Mhm.
argue of the embedding of a sequence of of, of tasks, probably
Mhm.
you would get a good example of an application. So it's pretty much in the beginning of studying this.
So if you ordered your items in terms of difficulty to begin with, I mean, that would align exactly.
At least you expect that, yes.
Yeah.
And this is a
And then the,
constraint. This is a constraint that is you don't require that they are ordered by difficulty only. You expect something on the discrimination and the way the discrimination is diminishing or increasing over the
yeah.
series. Yeah, there is a constraint in this cascade of discrimination. Yes. At least
And then
in
lastly, on asymmetry, Lee mentioned this too. We have in my lab we've worked on this and always failed. We tried to do really simplistic things and they never quite work out. I think your model's very elegant. And
Thank you.
the reason we were interested in it is there's all kind of asymmetry in choice. I mean, the literature is filled with that, and we think of preferences as choices. And most of the things that we model with the G-gum are in one way, shape, or form a kind of generalized choice. If you look at the choice literature, there's a lot of work on asymmetry and choice. So I think that model would be really important. The one thing that we always that I never liked about anything we tried is just like the 3PL and cumulative model kind of changes the meaning of an item location.
Yes, of course.
Mathematically.
Yes.
That same thing happened with us all the time. It's like, okay, delta in the G-gum doesn't represent where the item's located anymore.
Yes,
It's a complicated function of delta.
Absolutely. And the very same problem, you're absolutely right. The very same problem exists, of course. As soon as you get into asymmetry, you have this problem. And also, even in the symmetric case, in the 2PL, you have the very same problem. In the 2PL, you may get an item located more on the right, actually to be easier on the left because it may have a very low slope, for instance. And so being on the right but having a low slope, it has a success rate, a success level that is higher than an easier item. So the location loses its sense as soon as you have other parameters. Actually, it's all a matter of interaction between parameters in the model.
Yeah. Well, I don't know if there are other questions out there for you, but thank you so much.
Thank you for the discussion.
For answering my questions and for staying up late.